Hey Dad, so if you remember at the end of the last video I was showing you this circuit right here where I was using the EEPROM to take an address, 8-bit address, and then light up these LEDs based on the value within that. So now I'm going to take it to the next step, which is these LEDs really don't do anything, but if I were to take this out and put a 7-segment display in here, it might make more sense. And that's what the goal of having this was just to drive that 7-segment LED. So what I'm going to show you now is actually how I did it, because I did some, for me anyways, very clever tricks. I don't have an electrical engineering degree, so anything that I can do with this type of stuff is just by rooting around on the internet and looking at data sheets and on chips and using my programming skills as applying it to electrical engineering. Probably not the best way to do it, but it's fun. So the 7-segment display that I'm using is a common cathode, so common ground, and that's the middle pins right there on both the top and the bottom. And then these other 8 pins light up all of these segments for the digit and the decimal point. So you can see how I would be able to take the output from the EEPROM, which when I showed in the video was lighting these 8 LEDs, and instead send it over to light up these 7 segments. Now the limitation that I had at the beginning was I was thinking I was going to have to use 3 EEPROMs, 1 for each digit. And I mentioned on the last video that it seemed kind of wasteful to only store 10 digits 0 through 9 on an EEPROM and then have to have another one for the second digit, another one for the third digit. So I started thinking about it, and I was trying to come up with a way to use this one output that can light 8 different lights to power all the different digits. So after a lot of thought and wasted paper and just going through data sheets of chips and stuff like that, and then also harkening back to that first video where I created a clock that just kept pulsing, and then I was storing data in the register, and I was lighting up LEDs just based on the counter. Well, I started thinking about it, so I built a clock that just pulses and took that output and sent it to a JK latch, which basically is a 1-bit piece of memory. And so whatever I put in and then execute the clock, it will hold that value until we turn the power off or I put something else in there. But one of the interesting things about this JK is that if you put both inputs to high and then cycle the clock, it will just toggle the output. So if it's on, it'll go off. If it's off, it'll go on. And then if you take the pulse from the first JK latch, every time it comes on, and you connect it over to the clock for the second JK latch, what you will get is this LED is going on and off with every pulse of the clock. But this one is only going on and off with every on pulse of the first one. And what that gives us is a counter. And if I hook my power up here and turn this on, you will see that's exactly what it's doing. 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And that then gives me those 2 extra bits, because if we look at those bits here, we've got our 8 bits here, and then I add these 2 extras, which gives me either all zeros, which will start out at 0 and go up to 255. But as soon as we set this bit, then it starts at 256 and goes up to 512. And then when this bit goes off but this bit goes on, it goes from 512 up to 768. So we have 3 banks now of 255 or 256 addresses that we can store which digit is going to be represented with that value, and we can then show it in, so the first bank from 0 to 255 will show the ones place. The one from 256 to 512 will show the tens place, and from 512 to 768 will show the hundreds place. So again, programming that or getting that access, that's fairly simple, because again, I've got these 2 extra bits, and I would just send them over to the EEPROM, and it would give me the digits that I need. But then the conundrum is, how do I take all of that and make it display to each individual LED? And so, remember I mentioned that I'm using a common cathode, so the ground. So what I came up with is this, the little truth table here. So for those 2 extra bits, when they're both off, I want an output that's low and everything else to be high. When the value is 1, I want the second to be low and the others to be high. And when the value flips over to 2, the second bit is high and the first bit is low, I want the third to be low and everything else high. And I didn't do anything with the fourth one because I've only got 3 digits. So with that truth table, I can actually have a low, low, and low, which will provide a ground to the 7-segment display, completing the circuit and turning on that digit. When the high, so if you imagine that, I plug into the truth table here, when it's a high, this is going to be 5 volts going into the ground, and all of the segments that are lit are going to be 5 volts. There's no potential there because they can't get to the ground. But once this becomes low, then all of a sudden it's grounded, and all of the segments with the connection to the power will all go on, and then you'll have whichever number you want lit. So I was trying to figure out how to get this so that I could actually convert this over to this. So with this truth table, I was able to design a little circuit using an inverter and NAND gates. And NAND gates take 2 high signals and convert them to a low. If any one of these input signals is a low, this is going to be high. So with that knowledge, all you have to do is figure out how to get both of these high when you want this to go low. Anything else, it's going to be high. So I brought the 2 inputs from the LEDs in here and I pathed them off, branched them off, and created an inverted signal for each. So at any time, I have 4 signals for the 2 inputs, and it's always the opposite, the input and the opposite, and then the other input and the opposite. And so if you look how we hook this up, now you look at the truth table here. If we're low and low, we want the first one to be low. So that means if we want this first output here to be to be low, we need to input 2 high signals. Well, that's the 2 inverted inputs. So if I take those, run them over to that, I get a low there, everything else comes out high. Same thing with the second one. We want it when there is a high signal on the first and a low signal on the second. So the first one just goes straight across because it's going to be high, and we'll use the inverted on the second so that it's also high because that's going to be low. And we do the same thing with the third. And so that got me to what I wanted right there. I can actually, as I'm scrolling through these values, I can then get out my ground state that I can put on my 7-segment display. And here is the result. So this chip here is the JK latch. This chip is the inverter that inverts the off to on and on to off. And then this is the 4-input NAND gate so that I can get my outputs. And those outputs are coming out here, here, and here. And so you see how I turn on the numbers one at a time, and I've actually got the anodes hard-coded to the positive just for this display. I haven't hooked it up to the EEPROM yet, but that's coming next. So the only problem that I see with this is that that's not really how we read numbers. That looks like 1, 2, 3 spelled backwards, but really what it is 321. So how do we fix this? Well, we go to our timer and we increase the time. And once it gets going fast enough, it looks like a solid display. And something that's interesting in doing this, I figured out this. I don't know if you've ever seen like a digital clock through the LED digital clock through a fan or like through an old camera, video camera. You always see the digits wobbling and making weird patterns, and that's exactly why it is, because this is actually not a stable image. It's actually that, but very fast. And so with this, what I can do is go back to the EEPROM, put in the bus of 8 bits, put out the 8 bits to the 7-segment displays and connect them all together. And then add the 2 extra bits to change the registers. And what's going to happen is, let's say we have a 255 all ons coming into there, and the first thing it's going to do is when the first bit is 0, it's going to go to the EEPROM and it's going to say, give me the digit for the ones place of 255, and it's going to output the signal for a 5. Now that output is going to go to all 3 digits, but because this is the only one that's on, you're going to see it there. Then it's going to cycle to the next counter and it's going to say, okay, give me the 10th digit for 255, which again is 5, and it's going to go out and get sent to all of the digits, but because the middle one's the only one that's on, that's all you'll see. And the same thing when the counter goes again, and it's going to be, give me the 100th digit for 255, which is going to put a 2 out, lighting all these enabling all these segments for a 2, but because this is the only one that's on, it's the only one you'll see. And if I do that fast enough, you will have your display. So now all I have to do is figure out how to use my Raspberry Pi to program this EEPROM, because I really don't want to do that by hand. That's 768 entries. I could do it. I'd probably make mistakes. But the good news is I don't have to do it once, because it's an EEPROM and it never goes away, even with the power off. So, but that's a project for another day. Just having fun here, learning a whole bunch, and it's really interesting. It's really it's really motivating. So, anyways, thanks for watching.